14.2 Mass Systems and Pulleys. A mass system is a group of connected masses that are pulled together by the same applied force. For example, you could imagine a train which has many different cars, all which are different masses along the train, but they're all pulled together by the same force and connected. A simpler mass system would be just two masses. We'll call them mass 1 and mass 2, connected by a single rope and pulled by a second rope by an applied force. The acceleration on a two-mass horizontal mass system can be calculated. And when you're calculating it, you determine it by imagining that the system is being pulled by a net force acting on a single mass. And the mass of this single mass is the combined masses of mass 1 and mass 2, or mass 1 plus mass 2. So instead of the two masses being connected, imagine a single mass, mass 1 plus mass 2, being pulled by that same applied force. So the acceleration of this system is the net force divided by the combined mass, mass 1 plus mass 2. We're going to look at several types of mass systems. For example, the first one and the simplest is two connected masses pulled by a rope on a horizontal surface. We'll also look at pulley systems. One pulley system might have a mass on a horizontal surface being draped by a rope over a pulley with another hanging mass. In pulley systems, instead of an applied force, often the force is gravity pulling the whole system down. There's a special pulley system that we'll look at today called the Atwood's machine, which is two masses draped over a single pulley. Both are hanging, and the only forces on the system are the force of gravity. But we'll start with a simple example, looking at the two-mass system on a horizontal surface. Mass 1 is 20 kilograms and mass 2 is 30 kilograms. The whole system is being pulled by an applied force of 300 newtons. But there's friction in this system. Force of friction is pulling back on mass 2 with 100 newtons. Mass 1, being lighter, experiences less friction. It only experiences 75 newtons of friction. To calculate the acceleration on the system, first we need to find F net as if the system was made of a single mass with 20 plus 30 equals 50 kilograms. The forces on the system are then the 300 Newton applied force and the two forces of friction, 100 newtons and 75 newtons pulling it back. So F net is 300 minus 100 and minus 75. This gives a net force of 125 newtons. The acceleration is net force over total mass, m1 plus m2. So the acceleration is 125 divided by 20 plus 30, which is 125 divided by 50, which gives an acceleration of 2.5 meters per second squared. We'll keep this acceleration because we're going to need it for the next part of this example. You will also be asked to calculate the tension in the rope between the two masses. The connecting rope, which is rope A, and to do this, you must consider the two masses separately again. If we consider mass 1, for example, which is 20 kilograms, it has a force of tension being pulled to the right, and the force of friction to the left is opposing it. So the net force on mass 1 is force of tension minus force of friction. We can rearrange this for force of tension. Force of tension equals the net force plus the force of friction. Net force is mass times acceleration. So this is ma plus force of friction. So we have 20 times the acceleration of 2.5 plus the 75 newtons, which was friction. This gives us 125 newtons for our force of tension. We'll hold on to this number for a minute because I want to show you what the force of tension is on the rope coming out of mass 2. Mass 2 is the 30 kilogram mass. It's being pulled back by a force of tension as it drags mass 1 along. It also has 100 newtons of force of friction and an applied force being pulled in the other direction. So the net force is the force applied minus force of tension, also minus force of friction. There's 3 forces. Rearranging this for force of tension, we get force of tension equals force applied minus F net minus force of friction. Force of tension is the 300 Newton applied force minus mass times acceleration minus the 100 Newton friction force, which is 300 minus 30 times 2.5 minus 100, which gives us a force of tension equal to 125 newtons. The force of tension pulling mass 1 is 125 newtons, and the force of tension that mass 2 is using to pull mass 1 is 125 newtons. By Newton's third law, this makes sense. The force of tension on either rope should be the same because it's the same rope. The rope used to pull is also the rope that's used to pull back. It doesn't matter which mass you use to calculate the force of tension. They both will give you the same result. I recommend using the easier mass. For example, mass 1 was easier because it only had 2 forces acting on it instead of 3. The back mass in our mass systems will usually work better than the front mass for this reason. We're going to look at a second example using a pulley. Atwood's machine was invented in 1784 by George Atwood to confirm some of the laws of physics that we're studying today. Atwood's machine consists of 2 masses draped over a pulley, where the only forces on the system are gravity, pulling the 2 masses down. For a system of masses draped over a pulley, you can imagine the system flattened out. with the force of gravity acting as applied forces. By flattening out the system, it makes our calculations a little bit easier and more similar to the earlier example, which was flat. Mass 1 is being pulled down by a force of gravity, we'll call it force of gravity 1, and mass 2 is pulled down by force of gravity 2. If you considered a flattened out version of this, mass 1 and mass 2 are horizontal to each other. Mass 2 is being pulled back by its force of gravity, and mass 1 is being pulled back by its force of gravity. If the force of gravity on mass 1 is greater than the force of gravity on mass 2, then the system will accelerate towards the first mass. It's heavier than the other, so it makes sense that it would pull more. If it's the other way, if the force of gravity on mass 2 is greater than the force of gravity on mass 1, the system will accelerate towards mass 2. Mass 2 is heavier, so it pulls more, which makes sense. Here's a real example. We'll have mass 1 as 10 kilograms and mass 2 as 5 kilograms. Since 10 is greater than 5, we know the system will accelerate towards the 10 kilogram mass. So the 10 kilogram mass will accelerate down, and the 5 kilogram mass will accelerate upwards. The force of gravity pulling the 10 kilogram mass is down, and so is the force of gravity on the 5 kilogram mass. But when we flatten out the system, the 5 kilogram mass is being pulled to the right by its force of gravity, and the 10 kilogram mass is being pulled to the left. I'm not going to put directions on these because we know that it's not actually left and right, it's both down, but for your purposes of your calculation, treat them like opposite directions. The force of gravity on the 10 kilogram mass is mass times acceleration due to gravity, which is 98.1 newtons. The force of gravity on the 5 kilogram mass is 5 times 9.81, which is 49.05 newtons. This means the net force on the system is the subtraction of the two opposing forces, which is 98.1 minus 49.05, which is 49.05 newtons. The acceleration of the system, then, is F net divided by the total mass of the system, which is 49.05 divided by 10 plus 5 is 15 kilograms, which gives us an acceleration of 3.3 meters per second. So the 10 kilogram mass is accelerating down at 3.3 meters per second squared, and the 5 kilogram mass is accelerating at 3.3 meters per second squared up. We'll use this information to calculate the tension in the rope connecting the two masses. Again, like in the previous example, you only need to look at one of the two masses to find the tension in the rope. They will both give you the same result. For this example, I'll only calculate it once, and I'll look at the force of tension on the 10 kilogram mass. Remember, the 10 kilogram mass is accelerating down, and the only two forces acting in it are tension and gravity. So F net is force of tension plus force of gravity. We'll keep the plus there because I'll use the negative of the acceleration and g to make it work. Ft rearranged is Ft equals F net minus Fg. F net is ma, and Fg is mg. So force of tension is 10 times negative 3.3 minus 10 times negative 9.81. The negative in the 9.81 is why I added force of gravity earlier, because I planned on putting the negative in the acceleration. Now remember, since these two accelerations are down, they must be given a negative sign in order for the calculation to work out. This gives a force of tension equal to negative 33 plus 98.1, which is a force of tension equal to 65 newtons. Up.